Hi everyone. In this video, I'm going to demo my Google Colab notebook on Jax. We'll go through the setup, understand what tensors are in Jax, learn how to create arrays, generate random numbers using Jax explicit PRNG keys, and then cover core tensor operation like broadcasting, reductions, reshaping, and concatenation. At the end, we'll preview why linear algebra, especially matrix multiplication, is central to deep learning. Let's start with import jax.numpy as JNP. So here the whole topic is about matrix multiplication with shapes. So this first code cell demonstrates the matrix multiplication using Jax NumPy API. And um, jax.numpy, which we import as JNP. In the first very line we can see, I define matrix A with a shape of 3 rows and 2 columns, and then matrix B with a shape of 2 rows and 3 columns, and then multiply them using add operator. We can see like add operator. The key rule is the inner dimensions must match. So if the A has like 3 rows and 2 columns and B has like 2 rows and then 3 columns, then the inner dimensions of 3 and 3 or these should match. After running, we can see the resulting matrix and shape check printed at the bottom. The point we can see like printed shapes and the final results are 3 cross 3. As I said, the inner dimension should be same. So this is the result matrix. And here, if I have to say this notebook overview, this markdown cell is the title and table of contents. It shows the full roadmap, tensors and operations, linear algebra, and some autodiff, chit vmap, and even building neural network, and even building your neural network from scratch. In this particular notebook run, we'll mostly cover the early parts, tensors and operations, and we also start the linear algebra section. Next cell is introduction to Jax. Here is a quick introduction to Jax. Jax looks like NumPy, but it adds powerful features using in deep learning. Automatic differentiation using grad, and then JIT compilation using JIT for speed via XLA, and vectorization using vmap for batching. Jax also strongly encourages functional programming, meaning we prefer pure functions with no hidden side effects. This is important for transformation like JIT and grad. Next, at first, we'll go ahead and like install Jax. In this cell, installs Jax in Colab. If you're using a CPU runtime, the default install is enough. If you switch Colab runtime to GPU, there is also an optional GPU install line you can uncomment. So yeah, this is the one. So if we like just uncomment is, we can run if the option is GPU. Otherwise, this one line should be enough. Next is importing the core Jax libraries like Jax, jax.numpy, and also like numpy as JNP, and the main transformations like grad, JIT, vmap, random, and we can also import numpy, matplotlib. Then we go ahead and print Jax version, the available devices, and default backend. On my run, it shows CPU. Yes. But if anyone is on GPU runtime, then they would see GPU device listed. Next is tensor fundamentals. And this section explains what is tensor. Basically, a multi-dimensional array A scalar is zero dimensional with shape as given here, and vector is one dimensional with like shape. Matrix is two dimensional with rows and columns of 2 cross 2, and then 3D tensor is adds another dimension, so and its shape is as given here. In deep learning, getting comfortable with shapes is extremely important because most error comes from shape mismatches. And then let's go ahead with creating arrays. Here, now we move into creating arrays in different ways using Python-less built-in creation functions like zeros and ones, and random generation using Jax keys. So this is the core cell, and we can see the output saying scalar is like as given, like 5 shape and also the dimensions. And then creating a scalar tensor. So here I go ahead and create a scalar using jnp.array with this input, and notice the shape and the number of dimensions, and yeah, this is the output. Then we'll go ahead and yeah, similarly, as I said before, like similarly I have created, like the vector is created, which is 1D tensor, and the shape prints as 5 comma like this, and meaning like there are 5 elements and the dimension is shown as 1. Sorry, previously I was supposed to point at this cell, and then yeah, this is for vector cell. And next is creating a, okay, 2D is also similar. We'll create a matrix using jnp.array and then shape dimensions. We can see the matrix is print and the shape is given as 2 cross 3, which is like rows and columns, 2 rows and 3 columns, and dimension is 2. Next, we'll go ahead and create a 3D tensor. This cell creates a 3D tensor. The shape is okay, once we print we'll get to know. And then we'll print tensor shape dimensions. Once we print, we'll get a 3D tensor with this, and we can see that the shape is 2 comma 2 comma 2, which is like depth, rows and columns, and dimension is count 3. Next, array creation functions. Here we use built-in creation function jnp.zeros, which is 3 cross 4, creates a 3 by 4 matrix of zeros, and jnp.ones of 2 comma 3 creates a 2 by 3 matrix of ones. So see, as we see in the output, it has created 3 cross 4 matrix of zeros and 2 by 3 matrix of ones. These functions are super common for initializations. Next is fill with constant. This cell uses jnp.full to create an array filled with a constant value. Here we have used, here it is 7, so it's useful when you need a tensor with a fixed baseline values like this, as we can see in the output. Next is identity matrix. Now I create an identity matrix using jnp.I with 4 as 4, and identity matrix shows up a lot in linear algebra, and they are useful for testing and for certain transformations. We can see the identity matrix in the output. There are like ones in the diagonals. It's like a 4 cross 4 matrix here. Next is ranges. So in this cell creates ranges like jnp.arrange of 0 comma 10 comma 2, makes evenly spaced integer by step size, and jnp.line space of 0 comma 1 comma 5 creates a smooth set of values between 0 and 1. I'll show it in the output later, using a fixed number of points. Line space is very common for plotting and numerical experiments. We can see the output whenever we have given a range of 0, 10, comma 2 with a space of 2 from 0 to 10, so 10 is excluded. So it says like from 0 to 10 with you know two space numbers will be generated like 0, 2, 4. If we say like line space, then if we give like 0 to 1 comma 5, then we can see the output like 0, 0.25, 0.5 till 1 with 5 elements. Next is random arrays with explicit keys. Now we generate random numbers the Jax way. Jax uses explicit PRNG key. So we start with random PRNG key of 42 as a seed. Then we split the key to produce a subkey. We generate uniform random values in a 2 cross here, random uniform values in 2 cross 3 shape. The key idea is no hidden global random state, everything explicit and reproducible. Normal distribution. This cell generates random values from a standard normal distribution, meaning mean 0 and standard deviation 1 again. See mean 0 and standard deviation 1. We split the key before using, so every random operation gets its own subkey. Next, random integers. Here we generate random integers using random.randint. We specify the shape as 3 cross 3 and bounds from 0 to 10. This is useful for synthetic data labels, simpling indices and so on. Next, why explicit PRNG exists in Jax? This why NumPy this markdown mainly explains the difference between NumPy's implicit global random state and Jax explicit key-based randomness. In Jax, key made random generation pure and reproducible, which works but better with like JIT compilation and functional programming. Next, core cell. Okay. Yeah. Here, this cell provides reproducibility. Two keys created with the same seed. We can see two cells produced with the same seed produces the same random values. Then we create a different seed and get different values. This is exactly why Jax randomness is reliable and debuggable. Okay. Next, let's go ahead.